Good afternoon, everyone. I am very pleased to welcome you to the Wide Band Gap session here at D60. My name is Mark Rosker. These days, I happen to be the Deputy Director of the Defense Sciences Office at DARPA. But today, I get to relive part of my past. 10 years ago, I was a program manager in the Microsystems Technology Office, MTO. And I was very interested and involved in wide band gap. That was my passion then, and I was the program manager for this program that we'll be talking about today for a significant period of time. DARPA is really all about the future, and we're very good at thinking about the future and creating the future, and sometimes recreating the future. Today we get to actually do something unusual for us, rare for us, and that is we get to think about the past, think about something that we did some time ago, and think about the lessons that we can learn from that experience. And that's what we'll be doing over the next hour. The DARPA program we're going to talk about was actually called the Wide Band Gap Semiconductors Program for RF Applications. Obviously, that's a mouthful, WBGS-RF program. It was a very a large program, involved hundreds of people, actually probably thousands of people were involved, all across the government. The service labs, each of the service labs had a significant involvement, and then a very large performer base as well. So everyone from academia through industry, FFRDCs, and so forth. It was a program that lasted for a very long time. It started in 2002, and it persisted, believe it or not, all the way until 2014, so 12 years. That's very long for a DARPA program. And it was a very successful program. At least I would claim it was a very successful program. It did some sensational things. But one measure of its success was that in 2016, a couple of years ago, when DARPA inaugurated an award that's called the Game Changer Award. This was one of the programs of all of the many, many programs that were available for this honor. This was one of the ones selected for the Game Changer Award because of its impact on the warfighter. So the program was a success. I think we can all celebrate that. And many people in this room were directly involved in it. But really, celebrating the success of the program isn't why we're here. This session, I hope, will be of interest to anyone who works with DARPA, who works around DARPA, even for someone who isn't quite sure what a wide band gap semiconductor is. It should be of interest, which leads me to my one slide tutorial. Okay. So here it is. So if you're not already familiar with solid state physics, this is the only chart you need to know to understand what we're going to be talking about today. So a semiconductor is a material that has a valence band, it has a conduction band, and it has an energy gap between them. A wide band gap material, like gallium nitride on the right, is one that has, well, a wider band gap than a traditional material like gallium arsenide, which is shown on the left. Or I could have shown silicon, which is another traditional semiconductor. So there's a wider band gap. Doesn't sound very important. It sounds a little esoteric, in fact, but it has tremendous importance. And it's the original reason why we and other people have been interested in wideband semiconductors for a long time. And we'll talk about those implications over the next hour. But really, I don't want to get overly focused in the semiconductor physics. I really want to talk about three themes, which I think will dominate the discussion with our panel today. And the first of that is, if you believe that this was really an exemplar of an outstanding DARPA program, how does a PM at DARPA go about building an outstanding DARPA program? And I would claim that that's critical to anyone who's attending D60, to any developer, to any user of technology. So we want to talk about some of the choices that we made, why we made those choices, whether they were the right choices over the last few years, over the many years. Things like we chose to focus on materials instead of going straight to devices. Was that a mistake, or was that the right thing to do? So as you sit in the audience and listen, I want you to be thinking about the choices that you would have made if you were the PM. Or even better, I want you to think about whatever the game-changing technology that you have in mind is for the future, and what choices you would make if you were a PM at DARPA. How would you organize your program? How would you make it successful? So those things, I think, will be of great importance. Even if you're not, intending to one day come to DARPA and be a PM and wear the government badge and get to have the great fun that I had the privilege of having, I think it's really important that the entire community understands what we're doing and what our constraints are. DARPA works in a community, in an ecosystem, and collaborates with that community very, very frequently. So in a sense, I would say, even if you don't want to be, all of you are DARPA PMs. So the second theme that I want to talk about is very much related to the first one. It's transition. So I would claim that transition is something that is absolutely necessary to be part of an outstanding program. You can't have a good program without it. But the thing about transition that I don't think is obvious is that transition is not something that is considered late in the program. It's something that is very much considered, needs to be considered throughout. And in this case, I think you'll see some of the discussion we'll be having. What to do with the technology, where it should go, how it could affect the warfighter was something that was thought about even before the program started. So from before the program started through after it was even completed, transition has been very central. So again, if you're thinking about the program that you're interested in, I want you to think about how it will affect the warfighter and how the technology you hope to develop will lead to something that changes, is a game changer for the warfighter. And the third and final theme that I think is going to come up again and again is actually niches. Because niches are often where you find DARPA having its greatest impact in transition. So let me explain what I mean. Wide band gap semiconductors, gallium nitride, is really an example of a niche application. We talked in the other room just a few minutes ago about Moore's Law and silicon. And we probably saw a cell phone or two talked about in that discussion. So there's no gallium nitride in my cell phone, not today, maybe in the future. That did not stop DARPA from investing in that technology. So far, the implication on consumer electronics has not been very much for gallium nitride, but its implications in the military sense have been enormous, as again, I hope to talk about today. So communications, radars, electronic warfare, and so forth. So if you're interested in having an impact, niche technology is not necessarily a bad thing. Sometimes it's a really good thing, but not all niches are equal. So when is the right time, if you're thinking about your technology, when is the right time to be investing in a niche, and when is it perhaps not a good idea? Okay, so for our discussion today, which we'll be getting to, I have an extremely distinguished panel of experts, and I think we're very fortunate to have them. I want to say a couple words, though, about how we're going to be organized. So we've divided the day in the hour into 3 segments. And we're going to talk about each segment. And before each segment, there will be a video which will introduce the topic and will describe and help motivate the discussion that we have. So the first thing we're going to talk about is the past. We're going to turn the clock back to roughly the year 2000. We're going to think about why the program came to be, what motivated it, and what its purposes were. Then we're going to talk in the second segment about the program itself. What did we do? What was hard? What did we overcome? What were the surprises? And then finally, in the third section, we're going to talk about the future, which means where does this technology go? And what is it that DARPA should be thinking about now, given where we are today, looking forward? Okay, and one thing I wanted to say, and I think by now you probably already know this, when we get to the end, we're going to have a Q&A session. Q&A will come from you all, and please use the D60 app to enter your questions, and we'll collect those, and in the last few minutes, use that time to go over that section. Okay, last thing I wanted to say before I introduce the panel is I get to stand here and represent to you the program, but a great number of people. Like I said, hundreds, if not thousands of people were involved in this program. These are the individuals who were PMs responsible for the running the program, but of course there are a wide number of people I can't represent. You'll be seeing a few of those familiar faces in the films that you're going to be seeing. Finally, let me now get to the heart of the matter and introduce the panel that we have. And our first panelist is the Honorable Zachary Lemnios. He is currently the Vice President of Physical Sciences and Government Programs at IBM Corporation. So Zach has many connections to the WBGS program, and I probably won't get them all, but here are a few. Even before the program started, when he was at MIT Lincoln Lab, he was responsible for a very important study that helped motivate the government investment in the wide band gap area, and we'll talk about that a bit. Later on, he moved to DARPA, and in fact, when I got to DARPA, he was my boss. He was the office director for MTO during one of the crucial periods of the wide band gap program, including the time when the program moved from phase 1 to phase 2. And then later on, after that, a later responsibility, he became ASD R&E. And so, in effect, he was the customer that accepted or at least the voice of the customer that accepted the first transitions of this technology into DoD systems. Okay. Umesh Mishra, Professor Umesh Mishra from University of California, Santa Barbara, the Donald W. Whittier Professor, is most illustrious member of the technical community who has really been one of the pioneers, maybe the pioneer, in gallium nitride development for a very long time. He's won a tremendous number of awards, too many to mention, but I will mention one or two of them, the Welker Award and the IEEE David Sarnoff Award for his work in gallium nitride. In the program, he was a performer. He happened to be a subcontractor to the Northrop Grumman team. And since then, he has been the CTO and co-founder of a very important commercial company called Transform, which was founded in 2007 and which sells gallium nitride products. Rear Admiral Douglas Small is also with us. He is the Program Executive Officer, the PEO, for Integrated Warfare Systems. He has been directly involved in two organizations that were really critical to transitioning the wide band gap technology. More than anyone else, I think he probably could be identified as, when we talk about the customer, he is the customer for this technology. So he was involved in the Missile Defense Agency and then PEO IWS. Unfortunately, Professor Dwight Strite, who was going to join us, and you'll find him in the program, was not able to come, but we're extremely fortunate to have as a last-minute replacement, and audible, as it were, Dr. John Zolper. Dr. John Zolper is currently the Vice President of Research and Innovation at the Raytheon Company. He, too, has many, many connections to WBGS, and these, like Zach, extend before his DARPA service. He was a program manager at ONR, who was funding gallium nitride efforts in the field in the pre-2000 timeframe. And when he moved to DARPA, along with Edgar Martinez, he developed the WBGS effort. He actually technically was never a program manager for the RF program, but he did run the companion program, which was the high power electronics effort. And then subsequently, he too became my boss and the office director of the Microsystem Technology Office. Since then, since leaving DARPA, he has been at Raytheon, and at Raytheon, he has been a primary sponsor and proponent of gallium nitride and gallium nitride development at Raytheon, and has been directly involved in numerous insertions. So I want to thank all my panel members for agreeing to participate. We're going to be doing Q&A almost the whole time, but with no further ado, I'd like to move on to the first segment. Go ahead.
In the mid-1990s, the United States Navy foresaw an emerging mission regarding theater air and missile defense, adversary weapon systems were achieving impressive advancements in missile standoff ranges. The Navy was in need of a new antenna array with enough sensitivity to detect and track objects at far greater distances than the current technology would allow.
Actually, if we go back to when the program was first conceived in sort of 2001, at that time the Navy was thinking about their next generation radars. They wanted to have more performance to do a new set of missions, missile defense missions, where they needed more power aperture gain out of a fixed aperture radar.
So gallium nitride offered a unique opportunity in the electronics realm for DARPA. There had been significant investments at DARPA and elsewhere in the optoelectronic side, such as LEDs and other emitters. And on the electronic side, it offered opportunities in advanced RF electronics, power electronics, and in thermal management that don't exist in, or hadn't existed in the other compound semiconductors. This program specifically addressed the RF transmitter technology enabled by the gallium nitride technology.
The way that it did it in the previous DARPA 3.5 efforts, at least the principal ones, were MMIC and MAFET. MAFET stood for microwave and analog front-end technology. When we started the MMIC program, all of the major areas that needed to be brought to maturity were really in a very, very embryonic state of development. There's a direct parallel between the MMIC program and the WBGS-RF program in that when we started MMIC, the gallium arsenide was terrible.
Well, you know, ONR was one of the first people to really take wide band gap seriously, and Max Schroeder gets a lot of credit for that.
From the original folks at ONR was the contributions of Max Schroeder, who was a program officer over at ONR, who really funded a lot of wide band gap semiconductor work for decades, really in the 70s and the 80s, as he tried to establish different sets of materials to deliver the capability that ultimately became gallium nitride.
And in the mid-'80s, that was the time when it became very clear the many advantages solid state had for phased array radars.
So here I was 20 years later with people saying, I've got this material that has a really, really large band gap. Now, I didn't really know, where it was going to be useful. But I had this gut feel that it was going to be really, really important, that we get the noise down further, we could handle higher voltages and higher currents. And so I funded it for that reason.
Okay, very good. All right, so now let's spend a few minutes talking about the past. And let me start, Admiral Small, let me start with you. And take us back a little bit and tell us a little bit more about that graphic that we saw. So there was a particular need for a theater air missile defense application. What can you tell us about that, and why was there a need for a new semiconductor technology?
Well, and I think that the earlier pioneers sort of saw the need for the materials side. I mean, from a capability perspective, I think what we saw was exactly what they said, is we needed to be able to detect fainter objects farther away, specifically for the air and missile defense type missions. And so we looked at everything from, much larger arrays, even larger ships, a lot of other things. But really when we came through looking at everything that was required, what we came down to was putting a SPY-1 sized radar on the existing essentially destroyer hull form. The only thing that could get you to the power aperture gain required for the sensitivity improvements required was the gallium nitride type material, which is basically what we proved out through the AMDR program.
Very good. Zach, maybe you want to say a few words. That study that I mentioned a few moments ago was sort of paraphrased in that chart. And it had a lot to do with DARPA making the decision to go forward. Maybe you want to add a few words about that.
Yeah, and actually I see Mark Hollis in the audience. And Mark, it was your group, I think, that did a key part of that. This program came at a really unique time. It was right after the MMIC program. the Air Force had figured out how to build small phased array for airborne applications, and gallium arsenide was key to that. The industrial base had taken off. That was kind of moving along at rapid pace. These new threats started to emerge, and the Navy was trying to think about how to incorporate solutions without having to build vessels, surface combatant vessels that had a high signature. And so we took on an effort at Lincoln Lab. I was at Lincoln at the time. This was before my second DARPA tour. I was at Lincoln at the time. We said, let's try to understand how to translate the technology promise of gallium nitride, or wide band gap in general, to the ConOps and system applications where that might have a really big impact. So we looked at this in the study, not so much from we looked at the technology pieces. We tried to understand what were the technology barriers that we really had to address. But we looked at it in the context of how would this actually transition into an application that could be fielded. And then the third piece, which came much later, which DARPA also solved, is how do you then, once you build those first prototypes, how do you then build an industrial base that can support this at scale? And that's the magic of DARPA. It's not just solving the technical problem, it's solving all the problems. It's building a community that nobody else can build. National Science Foundation couldn't do it. ONR had the foundational pieces of it, and Max was one of my mentors and a remarkable guy. He has an MG that I think he's probably fixed up by now. He's retired for a few years. But it's actually the magic of DARPA that can bring these communities together that you wouldn't see any other way, right? Because there's a program manager. Program managers have lots of passion, a little bit of money at play, but it's all the latitude to make it happen. And that's really what the study was about. It was to try to give DARPA some insight. And a few years later, I came back, and John and I worked together on this, and others did, and it kind of went on. We tracked your publications, you tracked ours, you tracked Mark's,
Yeah.
and we kind of knew the technical foundation. We were trying to put all this together, and it wasn't a simple story to put together.
John, you want to add anything? You were at ONR at that time.
Yeah, I guess to Zach, actually that's where Zach and I first met, was on that study. So we were on the TR module version of that study. I was at ONR, and the mission was basically you want to stand back farther, you want to see small things far away, right? And you kind of can't make the aperture much bigger than this, right? So actually that's sort of the back of the envelope, you can sort of solve that problem and say, well, the only thing I can really do is turn up the power on this amplifier in my array, but gallium arsenide is maxed out. And at that time, gallium nitride was exploding from LED technology. People figured out how to make gallium nitride LEDs. And electronicers like Umesh said, I know how to make transistors out of that stuff, right? So it sort of just took off. And so there's sort of the first question of the DARPA catechism was, what problem are you trying to solve? Missile defense, higher power aperture gain on a fixed aperture. What's new about your idea? Gallium nitride, the whole thing's exploding, but then flushing out all the challenges that came behind that was the key part of it.
You know, I remember that the briefing, I remember two briefings, one at ONR and the other at NRL. I think Jerry Borsick led the second one, and he just wire brushed us on what was, let's go through the power aperture, the gain equation. What's the trade space look like? And we went through the trade space of what was needed and how far was the technology from where we needed to be in order to achieve a particular sensitivity for a particular class of targets. And it was down to that level. Now, from a technology point of view, you probably wouldn't ask those questions. But this was a scrum to try to really understand the details. And that's what it took. I think that, and we kind of got to that point and further in some places.
So John, other than the naval application, were there other applications at that time, or did those develop later on?
So the way I think about it, that was the driving one, and I was telling the Admiral we had Captain Haggerty was pounding on her back because he said, my boss is telling me I need this radar next year, and then so that was 2000, 2001, and the Navy came out with their AMDR program 2010, I think, right, sir, something like that. But from RF perspective, I make the analogy to computing, right? Do you need more computing? And the answer is, you give it to me, I'll use it, right? So you need more RF power, whether it's EW, communications, or radar. Obviously, there's lots of system challenges in how you implement it, right. But you never have enough power. They always stand back even farther and see even smaller objects, right? And no one's going to turn that down. So, and same thing with the EW, which is the inverse problem. You stand back and you impact your adversary. So more power is always better. You're never going to have enough RF power from a sort of mission perspective.
Yeah, well, not only more power, but also more efficiency too.
Well,
so.
they come together,
Yeah.
yeah. Right.
Yeah, but that is the key. I mean, it's like the specific power, right? Because you also don't want to have to completely change out a power plant on a ship in order to incorporate this radar. Right. So the technology really did find sort of a killer application.
Yeah, to Mark's point, efficiency, and actually the curve we generated was actually based on ship power plant, right? You only have so much power available. How big can you make your array? What efficiency and what power can you support? And that sort of, well, we need that point right there.
That's right.
So, Umesh, take us back to that time frame and tell us how hopeless gallium nitride was.
Yeah, it was. And the problem with gallium nitride was, well, let's talk about the positives first. Gallium nitride LEDs, as John mentioned, had just come online, but it was filling a void, an obvious void. There was no blue light, there was no green light. So if you made a dim blue light and a dim green light, you could sell the thing. And then you could upscale it. You could start at low performance and go up in high performance. With gallium nitride electronics, okay, so that actually fueled the fire. We said, oh, wow, you can grow this material, not everything, at least you can grow the material. We can make transistors out of it. The problem is that with electronics, we weren't filling a void. I didn't know about this ship problem, okay? So I'm sitting out there on a blackboard or a whiteboard, and so we are saying, okay, the problem we're trying to solve is we're trying to improve something, but there is a solution in place. That's gallium arsenide. And it ain't standing still. It's going to get better. And so we're always trying to replace an incumbent technology. That's very, very hard. And it gets very hard when you have PowerPoint and the other guys have amplifiers. And so you're sitting out there trying to convince people that this stuff is good, and that guy brings, working widget. So it was hard, and we didn't have a substrate. We didn't know, what to grow on. Silicon carbide was also, this is why WBGS is not only gallium nitride, but silicon carbide was coming along as a substrate. So lots of things had to come together for this to work. And so, I mean, it was a bit of a hope and a prayer, and on the part of everybody, on the part of the performers, on the part of DARPA and ONR. I mean, people had to have faith in this technology to see it through, because along the way, anybody could have pulled the plug for a million good reasons, but they kept funding it for one good reason. And I think and then, it's kind of solved things out. But one big important point I'd like to state was what this whole effort told us is that if something looks awful, but you're not, just violating some fundamental laws of physics, go ahead and things might sort things out.
Umesh, that reminds me that, and this is off script, but it's kind of important. As I looked at this, and I've seen other programs the same way, similar programs, there's always going to be, who were the big decision makers, or what were the big barriers that you had to overcome? To me, there were really two. There may have been more, but the two that I recognize. The first is you got to convince an office director like John to actually take this on as part of their office portfolio, drive it, bring a program manager or program managers in to make it happen. And John, you did that, and others did that as well. But the other one, and we often don't see this, it's convincing a PMO or it's convincing a program office that the risk is now burnt down low enough, and there's a capability that exists in an industrial base to deliver this at scale without a whole lot of risk. And you may know what the band gap of gallium nitride is, may not, I don't know. Your acquisition exec may or may not know. But at the end of the day, you want to make sure that, okay, this magic dust that DARPA developed has a path to an operational capability, and that path has to include the entire infrastructure to deliver it, right? And that's replete in every DARPA program. You'll see that, right? Every DARPA program has got to include a way to take that technology and embed it in some delivery path that a program office can say, I want some of that, and I have an understanding what the risk is to get it, and I'm willing to take that risk. And in this case, that was a big bet. Because, I mean, you were publishing in Science, and we're trying to, okay, this is going to go on a combatant command chip, really? And it did.
All right, so that sounds like a really good segue. So let's now start to talk about the program. We'll move on to the next segment.
To understand the Wide Band Gap Semiconductor program and why it is important, we need to remember what a power amplifier is. Similar to how a person can speak into a megaphone to amplify their voice, an electronics power amplifier takes a relatively small RF signal in and puts a much larger RF signal out. A higher power radar can detect and track objects at greater range. GaN semiconductor materials looked like they could provide the needed power, but there were some very difficult technical challenges.
At the start of the program, we were working with little bits and pieces of semiconductor material, and we were lucky if we could get our hands on a couple of 2-inch wafers. Various groups were reporting, amazing results, huge power densities, but the problem is that those devices often degraded under test.
We need to go back to 2000 to understand the state of the technology at the time. The substrate technology at the time was very poor. The material that was produced by some of the U.S. crystal growers had a lot of defects and a lot of imperfections.
Material difficulties, all sorts of problems with them, traps, various other imperfections, very, very small wafer sizes to begin with.
And actually, when we first pitched the program, Edgar Martinez and I wanted to go right into making transistors and integrated circuits. And Dr. Tether, the director at the time, challenged us to show that the core materials were ready and could support that type of performance.
Well, I think it's the overall success of any program. I have found that when people are doing something very, very challenging, where the endpoint is going to be a long time away, that it's really great to have other endpoints along the way that people can focus on. Because if you're focusing on something that might not happen for 10 years, you really don't have the same drive if you have something that's going to happen in the next 6 months.
As we started, as we called those kind of go, no-go metrics, they were sort of the DARPA hard metrics associated with many of the DARPA programs. And I think that's really what makes the DARPA program so unique.
The DARPA milestones were very rigorous for just reasons.
I think if we would have followed the path of start demonstrating devices and integrated circuits without really focusing on material technology, I don't think that the technology would have succeeded. I don't think that we would have had enough insight into how to make integrated circuits using gallium nitride.
So we started the program at DARPA to go from sort of those hero demonstrations, sort of one-off devices that showed the device physics worked, to making really complete material capability, device capability, integrated circuit capability that was both high yield, high performance, and reliable.
But importantly, they focused the program, solved those materials challenges in the first phase, then worked on the device challenges, and finally worked on the circuit challenges. And that helped realize the technology at a maturity level where the transition community could really embrace it.
Good. All right. So let's talk about the program. And I just can't avoid looking at you, Umesh, because you're the only person on the stage who was actually a performer in the program. There was a lot of discussion a few moments ago about milestones. We heard Dr. Tether talk about how important the metrics and the milestones were. When we heard Tony Balstreri, who was one of the PIs, complain a little bit that they were too hard, maybe. Tell us about the program and how those metrics and milestones affected success, how you perceive them.
Well, at the expense of, being coming across as being too DARPA, too much appreciative of DARPA, I'd like to say that the biggest thing about a program is actually getting the metrics set right. Because if you set it as being something that can be easily achieved, you get what you ask for. If you set it to be completely crazy, then people think that, we'll just submit anything and then we'll mess with the metrics and confuse the people and then everything will be a success.
Did you say that? Did you
I'm shocked. So the way I looked at it was this was actually pretty spot on. And in the sense that, and I think, the complaint I had about the fact, not complaint, but the reality that I had about the fact that we actually had incumbents that we had to overcome. We had to actually, DARPA had to shoot way ahead of the duck. So, the performance actually understood that also. So I think that to repeat what Jim Milligan just said was, as far as I'm concerned at least, they were truly DARPA hard metrics, but they were not insane, and I think that, so once you started doing it, and then you realized that the program was big enough that you didn't have to carry all the water. The substrates had to come along and people understood that. The epitaxy had to come across, and there were metrics about epitaxy. As Director Tether said, there were metrics on simple things like what is the mobility of the electron over how big a wafer. So it wasn't, even though we were stepping towards a very tough target, the steps were pretty clearly laid out. So it was a great program, really pushed us.
You're not getting any more funding, no matter what you say.
I know. That's why I was like, God, if I start saying this, it's like a bit of a kiss ass. Yeah.
John, I wanted to ask you, I know at the time you were at DARPA, but now you're at Raytheon. And Raytheon was one of the performers. Tell me about their corporate investment and how, at the time, they leveraged the program to develop the technology.
Yeah, so Raytheon had been in gallium arsenide and sort of been tracking gallium nitride, and to some of Umesh's comments, people feel, well, it's not quite there yet, right? So I think we had started investing maybe a couple years before the DARPA program started, but over the last 15 years, we probably invested 150 million, 200 million, in addition to the government investments from Title III and DARPA and ONR and different activities. But I think a key, so it's a partnership and you leverage that, right? And Raytheon invested because it's key to our product. So we build radars, we build EW systems, communication systems. And by having this core technology in-house, it gave us that business discriminator for our customers, right? So there was a clear business reason to make the investment to enable our system solutions. But circling back a little bit to the metrics, I think a key point was there was a whole community in the government particularly that had been working in this field. So these metrics just didn't get generated in a room on a blackboard by one person, late at night or something, right? So there was a whole tri-service, so Army, Navy, Air Force working together with DARPA to think about this technology and what it was. And most of these metrics, there was an existence proof that you could do it, but there wasn't a proof that you could do it over large areas or do a repeatability. So we knew, the physics worked. We knew it wasn't, it was doable, but then the metrics that you helped flesh out and other people in the materials, do it over area, do it repeatability, have it measured by a third party. Typically the service labs were doing, actually validating the metrics. So it wasn't just a one-off, do it once and show you could do it. It was do it over area, do it over repeatability, have someone else measure it. But there was a real partnership there in working with the government service labs to do those, because there was a lot of the measurements were new, right? How do you measure mobility? How do you measure reliability? So there was real partnership there that was really key to developing the metrics, but then also, proving them out.
So the question I've always wanted to ask Admiral Small, when did you become aware of the program, and when did you really, in a sense, start to take it seriously and start to be very interested in the results?
So I had taken briefings on the effort, the DARPA effort, through ONR. I think was the ones that sort of, told us about what was going on. But interestingly, at least well, I think it's interesting, anyways. We'll see. We never specified that you had to use gallium nitride. We never specified any component, none of that. It was system level requirements, right? Along with all the illities and all the other things that you need to make it as part of a warfighting system. But it just came out that, gallium nitride, first off, was available for industry to be able to use it. So all of the investments across the board panned out. and that it was reliable and gave us the performance that we had to do. So, you know, I certainly was aware of the technology as it was coming through, but even at the start of the technology development for the radar, we still carried along gallium arsenide as one of the options. We always knew we wanted the better performance, but we had a lot of convincing to do of certainly my bosses that gallium nitride was ready for that scale.
Right.
And that was part of the trade study that we did at Lincoln. In fact, this was an interesting program because ONR code 30, I think it was code 30, and NRL had remarkable depth in the technology. You know, John, exactly to your point, right? And you know, it concerns me a little bit. I don't see that same depth in technologies that we're really concerned about today. It's not a comment on ONR or the services. It's just a comment on the fact that the commercial sector is driving a lot faster than what exists in the OXRs. But here we had a tech base. Again, Max Yoder was, when I was in graduate school, he was sending me material to finish my thesis. This guy was helping me out. When I got into the department, I helped him out, and it actually worked pretty well. We got to know each other really well, collegially and intellectually, and he had a team that really understood the details of this. And NRL was the implementer of a lot of this. That doesn't exist today in a lot of other technologies, and that concerns me a lot.
Umesh, I'm afraid that it sounds too easy. I want to hear about the problems. People always like to talk about the successes, but I want to hear about the problems from your perspective that happened, and whether there were times over that period of time when it looked like it was going to be insurmountable.
Oh yeah, actually, plenty of problems. We couldn't grow the material. That was the first problem. I still remember we grew the material and we had our first power result grown on, I think in 1996. And we did everything possible to get a result, but the material was heavily dislocated, you know, and people in the audience, a dislocated material, a typical material scientist will tell you that this is not a material that you should use. So, but this material came with dislocations to spare. I mean, it was just, I mean, it looked horrible. But the amazing thing was, we knew from LEDs that, hey, this thing actually put out light. I mean, and that was almost like a canary in a coal mine in reverse. That canary lived. So we were like sitting out here going, okay, if you can put light out of this material, then maybe we can make this work. That was one. So we went past that hurdle. Then came this very big problem called dispersion. What you saw in the DC characteristics of the material, unfortunately, did not translate to RF performance. And it turned out to be an absolute, it was a terrible problem to solve. The final solution turned out to be okay, pretty simple, just using the right coating passivation layer. The equivalent of silicon dioxide for silicon was silicon nitride for us. But you know, these simple solutions in retrospect, but you know, it's a kind of a very pinball, Monte Carlo approach to come to the problem solution. So using a material, making it useful with dislocations, solving this terrible dislocation, this dispersion problem was one. And then the other problem was a lot of other simple things had to be solved. We had to actually have, make just contact. This material was a ceramic, a near ceramic. Would we even be able to contact it? So, but luckily, gallium nitride actually is kind of God's gift to mankind. I mean, and it just kept cooperating, and you're like, why is this material working? And so you just kept, you know, we kept getting rope from upstairs, and we kept taking it. So I think one of the biggest, there were a ton of problems. You haven't
just hit the word reliability, not even once, I noticed.
Right, and the reason was I didn't care about it. All I wanted to do was get the performance, and then have Raytheon and Cree and, you know, and Northrop and all the other performance solve that one for me.
That's what a university guy can do that.
Right. So I was just focused, can we make this damn thing work? And if it works, then hopefully people a lot smarter than me in industry will make it work right. And that actually happens. So
yeah, we had the same experience. Dan, you and I had this experience with the development of SOI, right? The department, I think we put a chunk of money in to start that. There was no substrate. We didn't have, there was no material supplier. There was, I think TI had an oxygen implanter that would allow us to build buried oxides and some other odds and ends. But we made the investment at DARPA, challenged IBM and Lincoln Lab, partially and fully depleted SOI, just enough that those companies saw the value in it and made their own investment. And of course now it's part of our tech base, right? But DARPA didn't make the full investment. It was smart about the technology targets, and it just got it far enough that we burnt the risk down that somebody else would pay, right? And somebody else would pay because they saw the benefit of making that investment, and that worked out really well. It also worked out really well in silicon germanium. That whole tech base was DARPA seeded it, and it launched. But it was exactly that same situation.
So Zach, you're kind of touching on it again, and you said it a few moments ago, but I really want to give you an opportunity to say one more thing. We tend to think about the technical, we're technologists at DARPA, so we tend to think about the technology problems, but Admiral Small doesn't care about the technology problems. He really doesn't care at all. So beyond what we had to do technically, what other issues had to be overcome?
I think you're more than technologists.
Well,
I really think, MTO, before it was Microsystems Technology Office, was Microelectronics Technology Office, right? So we kind of ratcheted it up a little bit. And the technology issues are foundational. You have to solve them, but that's not the end game, right? It's not, look, I have no idea. Well, actually I do, but I actually don't quite care what's in my iPhone 7. I only care that it works. And I can refresh it every 3 years at a couple $100. It doesn't cost me much, and the tech base is actually pretty remarkable, but I don't think about the tech base much. In getting technology inserted, and I think where you're going is why does it take so long? You got to solve a lot of problems, and DARPA can bring communities together that don't naturally interact. Right? Like how often is it that a warfighter, actually a combatant commander, Joint Staff can actually sit down with a researcher at the bench and say, okay, this is what I need you to solve. Help me understand how you're going to solve it in a way that industry is going to take this on and do it at some cost that I can afford. I mean, all those equations have to come together. And if you think about the transition time for technology, the exemplar I keep coming back to is robotics, right? Our first urban challenge, the first DARPA robotics challenge is what, somebody help me out, 97 was it, 96?
2004 or something.
Well, 2004 was the urban challenge. The DARPA Grand Challenge, I think, was...
No, it was about 2004.
2004, and then the later one was 2007.
Yeah.
So tell me, how are we doing today with autonomous vehicles? Right, we're still, as an industry, we're still kind of working that. It takes decades.
Okay. I think
it does take time.
I'm getting the indicator we need to go on to the...
Well, Mark, can I just quickly circle back
Sure.
on reliability? You sort of mentioned it and we glossed over it, and I gave Umesh a hard time. It was fundamental to have the university understand the device physics, right? You really got to understand why it works or why it doesn't work, and they can explore all the design space of the transistor, understand those details. But then there was a big challenge on doing the real statistical reliability that the Navy needed to have before they could take it seriously, right? And that actually was non-trivial, and again, working with the service labs, but now you had a material that could run at very high temperatures, so you have to run it for a long time to get it to fail in a lot of cases. So there was a lot of working with, again, a lot of actually O&R and NRL to do the reliability and to generate all the statistics to convince someone that they can build a radar out of it. And DARPA took that on too, so they took on that reliability piece. So it wasn't just a hero sort of transistor or circuit, but it was that whole capability to address the transition. So I want to make sure we covered that.
Good, thank you. Yeah. All right, so let's move on. Let's move on to the third segment. And let's talk about where this technology has gone.
The technology that came out of the Wide Band Gap program was clearly very important to Cree. In fact, as I mentioned, the epi and the device structure that we really developed on that program are really very similar to what we have in commercial production today. And as we sit here today, we've sold over 20 million gallium nitride on silicon carbide devices. into a pretty wide range of commercial and military programs.
Result of the Phase 2 and Phase 3 programs, we were able to provide, well, DARPA provided sufficient funding and a teaming structure that allowed for rapid, accelerated advancement of the technology.
There were memoranda of agreement in place with 3 organizations: Office of Naval Research, the Missile Defense Agency, and PEO, Integrated Warfare Systems. There were actually 4 transitions.
Multiple transitions, many more coming today. Basically, every system we're proposing today has gallium nitride in it, not just Raytheon, but really all the defense contractors. And it's a performance and capability that is well beyond what commercial technology or applications require.
The DARPA Phase 2 and 3 programs really provided the foundation for virtually all of our gallium nitride products and foundry services.
From a commercial perspective, we have devices that have been fielded in 4G, LTE, telecom infrastructure, in a host of industrial, scientific, medical applications, wideband test equipment, and CATV, to name a few.
What is the next thing about gallium nitride? There's a lot of runway ahead of us on gallium nitride. There's a lot of things that, I think, will be done before we can close the chapter on gallium nitride. I think that the integration of gallium nitride with other semiconductor technologies is going to be, a major breakthrough. I think keep pushing the power densities and the thermal limits of the technology will really enable us to use the technology in different ways that we haven't used it before.
In terms of the next generation of high-power semiconductors, I think that it would be naive to consider the job done with gallium nitride and WBGS. It does not have as robust a foundry backbone as things like silicon, obviously, and other more mature semiconductors. So comparatively, it's really in its infancy, and as the community uses the technology and develops circuits and systems around it, they're going to identify all of the problems that need to be addressed.
So the DREAM program at DARPA that really takes on a lot of the lineage of the WBGS program follows on in a couple of important ways. Certainly WBGS was about establishing transistor technology that had high power density capability, which enabled it to operate with high efficiency over high bandwidths. DREAM takes all that heritage, but then it also layers on a focus on linearity.
One of the things that we see on the commercial side of the business going forward is an ever-increasing need in increased linearity, and that's one of the focus efforts that we have certainly within our internal R&D.
Gallium nitride electronics is not done. If you look at the device physics, there's easily another factor of 10, a DARPA hard factor of 10 to go from where we are today to the next step in technology. We can turn up the voltage, we can turn up the current, then we got to make it reliable. We have to integrate it in a complete module, integrate it in a thermal solution, and deliver that capability to the warfighter.
We really didn't know what we were going to find. But that's what DARPA does, That was one of those programs that he had go-no-goes to move himself up that way, but we didn't really know what was going to happen when we got there.
All right, good. So Admiral Small, let me start with you. Can you tell us a few things about how the Navy is using gallium nitride today?
Sure. I mean, we've certainly focused on the radar applications, and it is in certainly all of our radars, and any modern solid-state radars that come out are based on gallium nitride. Electronic warfare systems, we have gallium nitride across the spectrum in those. Basically, any RF system that comes out, I mean, we're really moving towards solid state for all of the reasons that have been highlighted. Gallium nitride is the key enabler.
Do you need more power? What do you see down the road as being the next thing that you're looking for? Power, linearity?
Yeah, I mean, I think we kind of hit on it. I mean, we'd always love to have more power. More power is more sensitivity, right? More power aperture gain. What can you get for the same amount of power in and cooling in, frankly? What can I get in terms of sensitivity? So given that set of constraints, yes, we always want more, absolutely. So yeah, keep charging. Yeah.
Zach, so let me turn to you. You were my boss. John was my boss too. So everyone was my Admiral Small. You're my boss too. So everybody was my boss. But from the hat that you were wearing when the program was ending, how do you think we did, and what could we have done better?
So you gave me the question a couple days ago, so I've been thinking about it. I think
You're not supposed to tell them that.
Well, of course they know. They know this. They get this. It's a smart group. So I think we did pretty well. I think you guys did pretty well. I think the team did remarkably well, and the performers did remarkably well. I think from a technology innovation perspective, it was a solid A, no question. Solved some really hard problems, moved from fundamental research to an operational capability with a tech base that emerged. You had catchers, you solved you tunneled through all these barriers that existed, not literally, but maybe figuratively. We developed a systems engineering skill set in this technology that really took us a long way and will take us still further. And I see that if the technology moves elsewhere, that engineering skill set is a big deal. John, your company is centered on that, right? There are a few other companies that have that caliber, but that's the preeminent piece. And from a national security differentiator, I saw it at my level in the building as a solid A. The thing that concerned me, and it's not this program, the thing that concerned me, this program was a bit sequential by design. And I think today we don't have that luxury. We just don't. We have competitors that are sort of at our tail, and we just, in many, many areas, don't have the luxury of doing the fundamental science up front, transitioning it to a brass board, transitioning it to a PEO that's willing to take a first demonstrator, transitioning to a surface vessel that's willing to paint its rack orange and do a few things, and transitioning. We got to think about how do we. The timeline was about right here because we had the core technology. We had this huge investment in the services and in the Navy in particular, on the operational side and on the science side. But going forward, I don't know that we actually have that luxury in a lot of areas that we operate in. And from my perspective, having been in the building, having been at Lincoln Lab and now in the commercial sector, this is something that really concerns me. It's something that should concern all of us. How do we transition ideas more rapidly than just sequentially? Sequential is easy. Even with the go, no-goes, it's logical. But we got to think, I look at Baidu, I look at Tencent and Alibaba and others, we all do. They don't transition sequentially. They move quickly. And you just sort of have to be prepared. So that's my only concern. Everything else was straight A's.
You didn't mention that before, by the way. When you were the office director.
No, you had a little fear is good.
Okay. All right, so I'm going to ask one last question, which I really want to get each of your opinions on. And it's about the thing I talked about at the beginning, niche technologies. So what does this particular, and kind of connects to what you said, I think, Zach. So what did this experience, the Wide Band Gap program experience, teach us about when DARPA should invest in niches and how should it choose those niches? I don't know. John, do you want to go first maybe?
Yeah, so I can start. I mean, I think start with the Helmholtz criteria and apply it to defense problems, right? So there was a compelling defense problem. So it's a niche in the fact that maybe at the time there wasn't a big commercial drive for it, although the LEDs were taken off on a different vector that we could leverage, right? So I think you should invest in niche technology where you can tie it to a compelling military advantage implementation, sort of at whatever level that is, right? Sort of the mission level. And then you have a technology idea or a technology path, that you can show what's new about my idea and what's the evidence that it'll work, right? So we had sort of the one-off device physics. We had those exemplars, and we had the application. So to me, that's a perfect niche. So I wouldn't worry about, is this a niche market? I would worry about, does it address a military application? Is there a compelling technical understanding of the solution space that we can move the needle?
Okay, thank you. Admiral Small?
Yeah, I think that's certainly I think the model that this effort went through, right, was there was a sort of a compelling need. I'm more concerned about the other aspects too. There's niche technologies that you need to be working on that we don't know what our compelling need is yet, but it could give us an advantage if we can very quickly get it out there. I think to kind of double down on the speed thing, back when we were going through this, we were in from an acquisition perspective, we were in a much different place in terms of how much risk we wanted to take in making some of these investments. That's changed quite a bit.
Right.
We're in a competition and we recognize it. So that's what I would say is, if there's niches out there that we don't know yet what the military utility is, I think the thing is the model of connecting the researcher with the warfighter with somebody who can translate. I think that's the model that will get us the new niches.
Umesh.
I still believe that investing in niche technologies, are critical, but I kind of agree with both Admiral Small and John that shouldn't worry too much beyond that as far as the military is concerned. But the thing about gallium nitride, which was so compelling, and the reason I as a researcher got into it, was I saw it as basically the second most important semiconductor after silicon. You could see it happening, and we didn't know how, but you just knew that its footprint was big. And so, you can start niche and you can end up huge. And that would be like the perfect storm in a good sense, And I think that there are many technologies on the horizon that could also do that. But I think if you could spot something that has more than one application, not necessarily right now, but you could actually dream up, it can go here and there. I think that's really worth investing in, because then speed happens, because industry comes in, and then everything else moves much quicker. If it's just driven for the niche, it just happens slower.
Zach.
Yeah, so niche is interesting, but I don't think that's actually, from my perspective, that's secondary. It's, DARPA bets on ideas and DARPA bets on people. It bets on performers, it bets on program managers. Program managers are relentless. They're just relentless. They'll never stop coming to you for money. They just, I have this idea, and performers, I have this idea. You gotta, Dan, you're laughing because you and I have both done this, right? So a good program manager sort of says, look, I have this idea. You gotta listen. You gotta listen to what the impact's going to be, and they have to put it in the terms of, what an office director can understand, what a warfighter can accept, what a PEO is willing to take on as risk, and what a company's willing to do. And be, have this dynamic range that nobody else has. The good news is you've got all the resources. The good news is you get plenty of budget. DARPA can connect anybody. DARPA holds a conference, everybody shows up, right? So you can bring communities together that you can't otherwise, and it's a really unique opportunity. So whether it's niche or not, I think that's interesting, but I think what's more interesting is the passion of the program manager, the passion of the performer, and the ability to describe the idea in a way that a warfighter, a user, can understand what the impact of the technology is without having to understand electron transport or whole mobility in an esoteric material system. That's all important, but at the end of the day, when you're on watch, that's not so important.
Okay. We've had a lot of fun, and I don't want to stop without letting the audience ask a couple of questions. So the first one is about commercialization. Globalization is what I meant to say. How should DARPA think about ensuring that the United States maintains a differential advantage in investing in technologies like GaN that are becoming global products, even long after the foundational programs have ended? That's a really tough question. I don't know which of you want to take that on.
I'll take it. My answer is double down. You heard it from a couple people in the video. If you look at the device physics and ask Professor Mishra, there's a factor of 10 or 20 in this semiconductor material, right? So why aren't we doubling down on that and getting it out in the next radar today, right? So that would be my answer. If you have areas, double down on them and run faster, right? Don't sit back and scratch your head. How's that?
You have to move fast. Yeah. Speed trumps.
Yeah.
In every domain, it trumps.
I agree. All right, I know that we're out of time. I apologize that we didn't have a chance to have more questions. We do have one small surprise on the way out, which I'll show you in a second. But I think it'd be a great opportunity to thank the panel for participating today.
It's great to see you again. Oh my gosh, this made my day.
I really appreciate it. Putting the videos together that you saw was exciting. John got to participate. Several other people got to participate. And we had so much fun. We have one more thing to show. So we can show that for anyone who's interested. Go ahead.
And just cut there. Forgot what I was going to say.
So I'm not sure I would go there.
Okay.
Did you want to say anything derogatory about the program manager?
He never dressed all that well.
However, the program that Rosker had that I thought was really the program that was the big deal, and this, not that this wasn't a big deal, this was a big deal, was his terahertz program.
And,
This wasn't on my sheet, you know.
I know.
Yeah.
We didn't want to make it easy.
Yeah.
I got to start over.
So I joined the Office of Naval Research in 1989. No, that's not right.
I've seen that tie, I've seen that shirt, I've seen that jacket.
Oh, that was crap.
Hold on, I'm sorry. What I need to do is get my glasses so I can see.
So I asked him, I said, well, how come the terahertz program is not the one we're talking about? He said, well, they all selected this one here. The director selected this one.
Thank you again.